There, anyone registering and attending the session today will receive a certificate of attendance, which many use for extended education credits. And I would like to remind everyone that we will be having an answer Q&A session at the end of the presentation. And so please utilize the question box from the controls on the webinar itself. And in addition to the video, when we post it on the website, there will be a PDF copy of the presentation material. So a lot of ability to follow up, even if you missed all the presentation. And as we are in the habit of doing, we like to start each webinar with a set of poll questions. And today is no different. So our first poll question is: transformer secondaries have notoriously high incident energy. It's a true or false question. There's no obligation, but we would appreciate your opinion and your feedback and weighing in on this particular question. It's one of those things where it could be tricky or it could be obvious. It's kind of up to you. So it looks like we have a quorum on this question. Thank you for responding. Here's how folks have weighed in. Looks like it's kind of a true is a heavy favorite on that one. Now, the answer to all these questions will be in our presentation, so don't go away. Then the next question is: typical overcurrent protection schemes, transformer using a protection relay would be coded as what? And so here are our choices. And again, there's no downside for guessing. Part of it's kind of extending your knowledge space and hopefully expanding the areas that you can improve based upon the material we'll be presenting. We do appreciate your attendance today. Hopefully you'll be getting needed education from the information we present. Okay, looks like we have a quorum on this one. Here's where the responses came in. Looks like 50-51 was a heavy favorite there. And then finally, on a 2500 kVA medium voltage transformer, primary fusing alone is enough to protect the operator working on a downstream system. Question, yes or no? And so I think we kind of gave it away with our other two questions. So appreciate you participating, and here's how folks weighed in on this one. Pretty heavily weighted towards the false side. And at this time, I'd like to pass the baton over to our guest speaker, Mr. Sam Reed, who is a principal engineer at Eaton Industries and is involved in new product development. Give me a second to pass the baton. Okay, Sam, you have the podium.
Perfect. All righty, without further ado, we'll get started. Just to give you a little bit of background on myself, I won't go through my long-winded bio here, but I have a background in mechanical engineering and physics. I did some post-grad work with SpaceX in vortex magnetic systems, specifically with their Hyperloop project, if any of you are familiar with that. And then I moved into Eaton and was formerly the lead application engineer for the transformer team prior to moving into being the principal engineer for the new product development division within Eaton's transformer product line. So just to give you a brief overview of what we're going to cover today, obviously, you know, as the title suggests, we're going to look at specifically the enhancements you can apply to specifically transformers and how to mitigate some of that low voltage arc flash incident energy. How do we solve that problem? But before I get into the AR VFI transformer, I wanted to just talk of some really high level concepts, something I call smaller, safer, superior. Really, how do we understand, you know, how we can use all different types of technology and componentry in order to create not only multi-functioning pieces of equipment, but safer pieces of equipment and ultimately, you know, more optimized designs. And one of those effects of that compact equipment I was just referring to on the total system design as it pertains to MV and LV for that matter. And then some examples of that, and then we'll go right into the arc reduction VFI transformer. And I have a few case studies to share as well as some real world arc flash events that we can show how this technology does actually play out in the real world. So just getting just kind of going again this high level, when we're looking at technological development, whether it's the NV distribution world, low voltage distribution, even things as small as printed circuit boards, cell phones, that type of thing, we see this trend of obviously the initial kind of breadboard aspect of developing that technology, refining that into something that is a little bit more robust and perhaps more integrated in its features, better laid out, more optimized. And then the final step being how we take that into a scalable but personalized scenario. And I'll hit on a few key high notes here that essentially highlight what we're looking for when we create these very custom products, but they're still very standardized, and how we can work to standardize our protection capability and then the integrated controls that we can put in some of this equipment. Obviously, in the NV distribution world, everything is very much engineered to order, very custom. But how can we leverage some of this standard design practice and some of these reoccurring features that we see in many different protection systems and distribution systems? How can we really leverage that to create something that is, I'll call it custom but standard? So how can we take both of those avenues? So as we see, basic technology, I'll use a cell phone as an example. All of us have these in our pockets nowadays. You can imagine, we used to have a very large cell phone that was just a phone. And as time went on, you shrink that piece of technology, but it's also becoming more capable. And now we've got things, obviously, everyone has a touchscreen phone in their pocket. You've got cameras on your phones. You have all sorts of different applications. It really enhanced by a long shot the functionality well beyond just that of a phone. And at the same time was able to really standardize on, in the industry on things like the chips or the camera lenses or the componentry that goes into that. So the idea here, and what I really want to hit home, is that there is a way to become multifunctional, to become integrated, to have all of this different functionality in one piece of equipment, but still have and drive that standardization and that practice, so we can create reliable and robust products that do still have that custom nature. So that's great as it applies to cell phones, but while we're here, we're talking about NV distribution specifically, and LV in some regard, and how that pertains to our jobs in the distribution world, and how can we take that same concept of the smaller, more compact, more integrated, and leverage that with our new technology, or these upgraded multifunctioning pieces of equipment. And one thing that I think we can all agree on here, it's very difficult to divine what is a good piece of technology, or what's the right methodology to execute. Protection is a very complex way. There's a lot of ways to skin that one and make sure that you're doing it correctly, you're doing it in the most efficient way. But I think what we can agree on is when something doesn't work or something's incompatible, it becomes very obvious to us. You might have a protection setting that it's overly complex. There, you were really trying to do a lot of redundant componentry, and it ended up being too complex to really be practical, or in some cases just be scalable or repeatable. It might have been a one-off scenario where that did work for this instance, but how can we really get that kind of cut and paste mentality while still having all of the necessary protection features and componentry that we're looking for? So, one thing that I've kind of come up with is how do we characterize this quote unquote good technology? How do we make sure that when we are creating, standard multifunctioning pieces of equipment, and we're trying to understand all the facets that go into that, not only the design and the physical manufacturing of that, but also the compatibility with your current system, the usability of that. I've got noted on here as well the intuitiveness of that product. So all of these features and aspects of this come into play when we're trying to kind of create this custom but standard package, something that can be utilized on a variety of systems. It can be tailored to fit your need. However, it's repeatable, and with that repeatability, we get our reliability out of that. So, of course, the number one function, whatever that application is for that piece of technology, I'll use the transformer as an example. We could add all sorts of protection capability and sensing capability, but if the transformer cannot transform voltage, then it's not good at that number one priority, that number one application of that piece of technology. So it's very important to highlight the fact that we've got consistent and reliable functions, and those core functions are met at the top of the list there. Then we can start looking at those other functions, the sort of secondary functions, if you will, that come after that core function. The second one to mention is the open or compatibility. And from a software sense, a lot of that folks might think like open source or intercommunicable. So you might have multiple protection relays on a site, and you might want to have the same type of relay all over your site so you have that compatibility. And that does not necessarily mean that it's exclusive to, single relay to single relay. You don't necessarily have to have the brand, but if you were designing something that said, say it used DNP3 protocol to communicate, you might want to make sure that your other equipment is also compatible in that avenue, to make sure, again, that use case is optimized and it's repeatable as possible. This third bullet here, this is really probably the most difficult one to quantify, and this is really that standard but custom note that I was kind of referring to earlier. The idea that you can kind of have I'll call it a kitchen full of ingredients, but you can make those different dishes as you see fit. But ultimately, that kitchen is standardized. They have the standardized parts. They have a standard practice for creating that dish. Ultimately, we're trying to create a recipe that is repeatable, but still scalable and can be personalized, can still be tailored to that application. And that's where we really get into some of this new technology, especially with microprocessor-based relays, where you do have the ability to kind of keep the hardware very similar to one another, but you can tailor in those specific protection settings, or activate certain different groups, or say something like a maintenance mode in order to tailor it to a specific setting in that specific application. And then the other two, somewhat obvious here, but the simple and intuitive nature of a product. Obviously, it's very good if something's extremely high functioning, but if no one knows how to use it and you don't understand how to interface with it, that doesn't necessarily make it a good product. So we want to make sure that as we create this multifunctioning sort of set of equipment, and as we meet multiple application requirements with whether it's a single control or a single piece of MV equipment, like a single transformer, we want to make sure that while it is compatible, it's easy to use and intuitive. And then, of course, well supported, right? You're going to need some of that engineering support, the technical knowledge. You wouldn't want to be handed this, this bag of parts and be told that it's up to you. You really do need some of that engineering support, whether that's coming from your manufacturer or if you're doing something like an analysis. And in the case of Easy Power, understanding how I can basically use something like an Arc Flash related software to easily analyze my system and best make that product then optimized and tailored for my application. So ultimately, what does this mean for electrical distribution equipment in the MV and the LV world? And this is really where I derive my smaller, safer, superior kind of commentary here. That the smaller is really looking to eliminate unnecessary redundancy, and I'm not referring to a double-ended substation type of redundancy. That's more of an obvious backup scenario, but things like multiple current sensors or multiple voltage sensors, when you're having overlapping zones of protection, you want to make sure that is as seamless and easily coordinated as possible. And ultimately, that's going to mean the fewest number of components without sacrificing your redundancy to a certain degree, but without overlapping or overdoing those certain, say, protection zones as an example. It also is going to mean least number of interconnections. So when we're talking about ways to do protection systems, obvious selections often are vacuum interrupters or vacuum breakers, where you have this electronically trippable component. You might have some sensors and some relaying combined in that. But if I'm going to have to tie all that in separately on site, it doesn't exactly make it not complex. I might have a very sophisticated protection system, but the execution of that protection system is extremely difficult. And perhaps I put a lot of work into my standardization, my cut and paste, and made sure I can repeat that on different sites, but that doesn't necessarily negate the physicality of putting that together and really creating it as a full package. Even testing it, going as far as to commission that equipment, can be a whole nother hurdle that we have to think about as we're talking about protection systems and multifunctioning pieces of equipment. Safer is a little bit more of an obvious one. Obviously, that there's really two sides to that. That's the low risk of hazard to the operator. So I've mentioned Arc Flash a few times already. That's again kind of obvious that we want things to be as safe as possible to work around. But then the other side to that is not just the operator, it's the safety for the piece of equipment as well. I've often encountered customers where, we are installing some means of protection and we're targeting, say, an 8 calorie per squared incident energy, something where, the user can now be in that gloves and face shield. And in most cases, even if it is a level 1 PPE category, they're probably still going to wear the gloves and face shield. Why wouldn't you add that extra layer of safety? So I have those same customers now, they'll ask, what is the value proposition to get from a level 2 where I'm wearing my gloves and face shield down to a level 1? Why would I need to do that if my users are already fairly safe? And obviously more safety for the operator is better, but there's another piece to that puzzle, and that's equipment safety. You can imagine that you would have maybe a low voltage assembly, and if I had an arc flash incident in there that perhaps was relatively safe to the user, their arc flash distance was, or their boundary rather, was enough where the user's in a pretty safe scenario, but my equipment damage is now still fairly high when I'm in that level 2 zone. And that's something I want to make sure that, from a standpoint of how do I get that equipment back online? What's the total capital cost? Downtime and outages is obviously another very big piece. So how can I increase safety, not only for my operator, but also for my equipment, and ideally increase the longevity of that piece of equipment as well, and keep my costs for fixing something like that as low as possible. And then Superior is a tad hand wavy, but that's the one we're all striving for. That's better performance, better price, better lead time, winning on all factors, and not always can you win on all of those. Obviously, price and lead time are, kind of go hand in hand, maybe negate performance in certain ways. A less performing piece of equipment might be lower price, lower lead time, versus a higher functioning piece of equipment might negate the other two. But ideally, we're really looking to, achieve as much of all three of those as possible. So really thinking about this smaller, safer, superior, and kind of driving home the fact that we really do want to ideally hit all these notes, especially as we look into these multifunctioning pieces of equipment. So I kind of already drove this home on the last slide, but I've got my black box here. This is going to be representative of our AR-VFI transformer in a few slides here. But really, what does this do now that we say we did achieve it? We're smaller, we're safer, we're superior. What does that gain me in terms of my equipment? Is it worth it? What's the real draw for me as the customer, as the owner, the contractor, to do something like this? And what this really means is, with these safer pieces of equipment, you can bring these connections, these higher voltage connections, closer into the building, or even all the way indoors. You can reduce those number of interconnections. You can essentially make a more smart integrated system that has it's less prone to failure, less maintenance points and things like that. And I'll go back to the printed circuit board analogy here for just a moment. If we're looking at a printed circuit board, and you've got, in the days of the cell phone, you had your cell phone in your pocket, you had your camera in your pocket, you had maybe a calculator in your pocket. Not everybody's carrying that around their pocket, but you get the point. I have multiple batteries to carry around. I have multiple buttons to manage. There's a lot of different pieces of that could fail, that could need maintenance, that might need new power supplies. As we integrate this equipment and we go to singular controls, the singular new modern phone or a singular piece of MB equipment, we can eliminate some of that unnecessary redundancy. And when I say unnecessary, again, this is not necessarily the backup transformer. This would be, I don't want a bunch of different switches doing the same thing. That's going to be too many components doing achieving the same function. So if I can eliminate, mechanical components, things like that are going to potentially add risk or add maintenance requirements to my system, that's going to be an overall benefit. And then, of course, the nice benefit that's sort of obvious is we're eliminating some of those unnecessary components, is we're going to get an overall smaller system. Hopefully that's going to reduce the cost, that's going to reduce the overall layout complexity, and ultimately the installation complexity. I mentioned the interconnecting, say, an MV switch and current transformers, relaying, doing that all on site. If we can find a way to consolidate that package into more of a single piece of equipment, that's going to allow us to reduce that headache on site and ultimately make the uptime, or rather the install time, greatly reduced and greatly much less complex. So just a few examples. These are some Eaton products, but you can find very similar stuff throughout the industry here. Medium voltage in the control assembly world or the motor control center world. You're obviously going to have your arc resistant MV switchgear. You're going to have remote racking, thermal monitoring. In the LVA world, low voltage assemblies, we're now seeing, in addition to the arc resistant, something arc quenching, where you're actually essentially creating voltage faults to quench that, to remove that fault from the scenario. They're doing the same, very similar stuff as MV, those remote racking, the thermal monitoring as well. But you also do see some, remote dashboards and things like that for interfacing with your products. And then on the transformer side, and what we're going to focus on for the remainder of the presentation here, we're really looking at some of this integrated equipment, these integrated vacuum interrupters. So I have the VFI, they're the vacuum fault interrupter. So integrating that into the transformer, integrating that overcurrent sensing, integrating that relaying, and also doing a similar remote racking or remote switching in those cases. And what we can do with that technology and how that technology being implemented in a transformer or in a substation lineup or whatever your MV gear is, how can that truly benefit you from an arc flash perspective? So I'm going to jump in just real quick on some of the current codes and standards. I say current, these are the sort of the latest and greatest, although a little bit old now, back in 2015 in terms of OSHA, the newer one, 1584 coming up here in just a moment I'll talk about. But essentially just putting these out here as a world, you're obviously going to have your arc resistant MV switchgear, you're going to have remote racking, thermal monitoring. In the LVA world, low voltage assemblies, we're now seeing, in addition to the arc resistant, something arc quenching, where you're actually essentially creating voltage faults to quench that, to remove that fault from the scenario. They're doing the same, very similar stuff as MV, those remote racking, the thermal monitoring as well. But you also do see some, remote dashboards and things like that for interfacing with your products. And then on the transformer side, and what we're going to focus on for the remainder of the presentation here, we're really looking at some of this integrated equipment, these integrated vacuum interrupters. So I have the VFI, they're the vacuum fault interrupter. So integrating that into the transformer, integrating that overcurrent sensing, integrating that relaying, and also doing a similar remote racking or remote switching in those cases. And what we can do with that technology and how that technology being implemented in a transformer or in a substation lineup or whatever your MV gear is, how can that truly benefit you from an arc flash perspective? So I'm going to jump in just real quick on some of the current codes and standards. I say current, these are the sort of the latest and greatest, although a little bit old now, back in 2015 in terms of OSHA, the newer one, 1584 coming up here in just a moment I'll talk about. But essentially just putting these out here as a reminder,